Thank you. Good. It's my pleasure to introduce Dr. Carol Ann Clayton at the Woods Hole Oceanographic Institution to present a CCS Distinguished Climate Lecture. Carol Ann received her bachelor's degree in physics from Brigham Young University and master's and PhD degree in aerospace engineering sciences at the University of Colorado. She's currently a senior scientist at the Woods Oceanographic Institution and the director of the Center for Ocean and Marine Atmospheric Sciences within the institution. Her current research includes air upper mixing, gas interaction and its impact on climate, and ocean impact on the global water cycle. Her research has been supported by many U.S. agencies, including OMR, NSF, NOAA, and NASA. And she has received numerous awards, too many to name, and that include the Presidential Early Career Award, NSF Career Award, and OMR Young Investigator Award. And she has also been serving on numerous national and international committees, such as the co-chairing the Climate Panel for the recent Decadal Survey, and the National Research Council's Board of Atmospheric Sciences and Climate, and the chair of the U.S. CLIVAR program in 2020. And CLIVAR is the Climate Variability and Predictability program. And she's the PI of an Airsea Flux product called Flux, and she's also the deputy PI for the recently submitted proposal called Butterfly for the NASA Earth Venture Mission 3. Finally, I just want to say that I've enjoyed working closely with Carol Ann in the U.S. CLIVAR Steering Committee during 2018 and 2019, and on the Butterfly proposal since 2019. And without further ado, please welcome Carol Ann to present the CCS Distinguished Climate Lecture. Thank you, Carol Ann.
Thank you, Tony. I'm going to work on sharing my screen now. When I was first asked to do this, I think it was pre-COVID, and I kept putting it off because I really much prefer being in person to give one of these. And then also, I knew it was a chance to come to JPL and meet with you. But it's kind of dragged on, and so that seems to be what we need. We just needed to do this. So I'm going to go ahead. I think you're seeing kind of a blank screen. Well, just a background screen at the moment. And I'm going to switch this off screen. All right. Hopefully you're seeing a full screen now of my title page. Is that correct?
No, actually, you had it right. You just switched it.
Now so you're seeing the
presenter view, yeah.
Oh, okay. It was right. Okay, so that's good to know that it remembers what I did the last time.
There you go. Okay, now it's good. Thank you.
Okay, now it's now is it a full screen? Yeah.
Yes, it is.
Okay, great. So again, it's really my pleasure to be talking with you today. I've gotten a few different comments from various people about what I should try to do up to and including sort of everything about how the ocean impacts climate in sort of a general sense and then very detailed on my research. And so I've kind of put those two things together, which sometimes it may be more successful or less successful. I anticipate that many of you will already know, much of what I'm saying just because I am trying to give some general context as well. But hopefully there's something useful for everyone. This is a picture that I took out on the Spurs 2 cruise, and I'll actually show a few results from that cruise. But I like this figure because, first of all, it was great weather, really enjoyable. It was in the tropical Eastern Pacific in summertime, so it was very nice. But you can see just the highly inhomogeneous nature of the clouds. There's a little rain event going on over here. And it sort of highlights some of the things that we're going to talk about. And again, if you have a question, it'll be hard for me to see if you just raise your hand. So if you just unmute and just shout it out, that's okay. That'll be easier if you have a big question. So one of the things that I actually end up doing quite a bit is I talk to a number of different groups I actually speak even on occasion with executive boards at large companies. I'm talking to one in July and it's on climate variability. And this is one of the things that I like to do that kind of demonstrates why we talk about the ocean so much. Because often when I'm talking with various groups and they don't think of the ocean really and how it interacts with climate and why it might be an important thing. But so this is now, these are two model simulations. The upper panel is surface currents, right? And the color then is the surface temperature. And so you can see some of the great features of our whole ocean circulation system. You can see the Gulf Stream. You can see the Agulhas currents and eddies, the circles here. You can see some of the waviness here, the tropical instability wave. Anyway, you can see a lot of different features. On the bottom is atmospheric water vapor. And I like to say our planet variability is really linked by water. And in fact, when I talk with outside groups about climate, we do talk about the fact that, that water is really the expression of the climate change that is going to be most perhaps impactful for people to see. So I like to demonstrate this just because you can begin to see how closely linked the two fluids, the atmosphere and the ocean, are linked by their water, and the variability and where the water is in the atmosphere and how it changes has a lot to do with, of course, the ocean currents. Although the atmosphere is moving much more quickly than the ocean. So one way that I like to think of what I do, which is really look at how the ocean and the atmosphere interact, is I like to think of it in terms of an engine. And I like to think of the whole atmospheric engine. So first we have the refinery, which is the sun. And then we have the sun's energy coming through the atmosphere. There's a pipeline. That energy is transferred to us, and it's a little bit of a leaky pipeline if you're thinking about how much energy actually gets down to the surface. But indeed, a large amount of the energy makes its way through the pipeline into the ocean and heats it up. And so the ocean then essentially becomes the fuel tank for the atmospheric engine. And then I like to relate the turbulent exchanges of moisture and heat between the ocean and atmosphere to the fuel injectors of our atmospheric engine. So the fact that the ocean on average is warmer than the atmosphere and also on average is more moist than the near surface atmosphere means that there's a lot of exchange of heat and moisture from the ocean to the atmosphere. And that creates warm, moist air. And it warms the air and moistens the air. And that warm, moist air then is basically the fuel of our atmospheric engine. And once we have that fuel injected into the system, then the engine itself is the wind, which is moving that warm, moist air throughout the system. And in return, the wind drives, through the turbulent exchange of momentum, drives waves and currents in the upper part of the ocean. And one of the things that I like to think about when we talk about that is that turbulent exchange of momentum between the wind and the ocean is really the brakes of the atmospheric engine. So we've got the fuel injectors and the brakes. And some of what we are trying to understand is sort of what is the ratio of the fuel injectors to the brakes. And this comes up particularly, people have come across this discussion in things like hurricanes and hurricane intensification. So there's, the injection of energy through the heat and the moisture exchange, but there's also the brakes on the hurricane through the loss of momentum to the ocean surface. And although I'm not going to talk about it today, really understanding how to model that exact phenomena, especially at high winds, is something that we're kind of lacking on. But today so this is just sort of an overview to place you in the context of why I'm going to spend a great deal of my time talking about the turbulent exchange of these products of moisture and heat and looking at the fuel injection. But as we see how this energy and moisture is exchanged between the ocean and atmosphere, one of the things that's a result is the global global water cycle. And this is a great paper by Matt Rodell. There's a companion paper by Tristan LeCouillier, which is essentially what they did is they took almost entirely satellite data. There was modeling reanalysis for atmospheric divergence, but they took all of this data, put it together, and then did a very nice quantitative balancing to try to determine what is the optimal correct flux that we think should be happening in the various components of both the water cycle and the energy cycle, because the linkage between those two is the latent heat flux. So it's an exchange of moisture between the ocean and atmosphere, but it's also an exchange of heat. So one of the things that they did that was really quite well done was putting those two together and balancing them at the same time, making sure that the latent heat flux was consistent between the two, and they were also very careful in taking uncertainties from the various products. And this is sort of the balance that has gotten this. And again, because if I were speaking to a bunch of oceanographers, we would spend a little while talking about why they use 1,000 cubic kilometers per year, but I just kind of go land people and let the and the oceanographers go, okay, all right. So in these units, the largest number that you can see here is the global ocean evaporation at almost 450,000 cubic kilometers per year. You can see it's larger than the ocean over ocean precipitation. That, of course, then leads to an advection of moisture over the land. There's the river runoff here, some latent heating, evapotranspiration as well from the plants and the land surface and lakes and so forth. So one of the reasons that I show this slide, and I will show this again because there's a second point that I'll make later on in my talk, but in this particular one, I do like to say this number right here is the single largest number in the entire global water cycle, and it has one of the largest uncertainties as well. And we're going to talk about that a little bit more. So again, the ocean is the fuel tank basically for our water cycle. We know that ocean evaporation supplies about 90% of the water vapor that eventually becomes rain and snow. About 40% of the rain and snow falling over land originated directly from ocean evaporation. The ocean also helps to determine the location of clouds and precipitation by influencing the atmospheric motions that move water, as we've talked about. And a number that I use because sometimes when I'm talking with various other groups, we talk about the importance of the water cycle sort of wherever you live on the planet. And one number that I do like to mention is that globally, about 70% of our entire freshwater supply is used for irrigating crops and providing food. So anything that changes then in our water cycle that affects our freshwater supply has like an outsized impact on crops and food production. So the other thing that we know, of course, is that the fuel in the tank is increasing. This is a figure from Church et al. In 2011. And what we see here, often I use this because I talk about what we see in terms of the change in near surface air temperature globally, and how that's changing, and how this number is a much more unambiguous indication. So this is of the extra heating that is being kept within our Earth system. Roughly 93% or so of that extra heating is going into the ocean. The other 7% is land, atmosphere, and ice heating. And so you can see these numbers, they're in zettajoules. So in fact, another number that we like to talk about is that that according to one estimate, the top 2,000 meters of the ocean took up about 240 zettajoules of heat energy between 1955 and 2010, but the temperature of the ocean on average only increased by about 0.1 degrees Celsius. And that's, of course, because of the high heat capacity of the ocean. I do like to point out to Grace that if the lower 10 kilometers of the atmosphere were able to absorb that same quantity of heat, the atmosphere would have warmed by an additional 30 degrees Celsius, almost 54 degrees Fahrenheit. So in a certain sense, we're fortunate that the ocean is absorbing that heat. On the other hand, if the atmosphere had warmed up by 54 degrees Fahrenheit, I don't think we'd be having discussions anymore about whether global warming is happening. So in a certain sense, the ocean is kind of masking that. But the ocean is, of course, connected to the atmosphere. And so as the ocean gains that heat, there are changes to the system. And this is just a more recent value looking at where the heat in the ocean is going, and again now comparing to top of the atmosphere from series, which is very similar to what we're seeing in the ocean heat content. So some symmetry there. So I then like to think about where have we been and where are we going, and this is partially because for certainly when I was in graduate school and then in my early career, sort of Airsea interaction in the 1990s, sort of the view of this is that the ocean just kind of, it moves water around and heat around, but it's just sort of a big, source of water and heat to the atmosphere. And it's not interactive in quite the same way that Airsea interaction was sort of like the atmosphere does things to the ocean, and then the ocean just is, a big swamp which you can take out heat and moisture from. And to a certain extent, when you look at very large scales, that's somewhat true. So on the left is the sea surface temperature, sort of an annual average sea surface temperature. And on the right is wind speed. And what you can see as you look at this is that when the SST is high, and the red's here in the tropics, the wind speeds tend to be low. And vice versa, as you look in the Southern Ocean, for instance, you get very high wind speeds, very, very cool SSTs. And so the sea surface temperature and wind speed are negatively correlated at these large scales. And in fact, if we do that more quantitatively, that you can see that if you just look at, again, at the sort of unfiltered wind speeds and sea surface temperatures, and you do a correlation between them, you can see that almost everywhere across the ocean, there's a negative correlation. In other words, the ocean is simply responding to the atmosphere. And so I would say that's a viewpoint that is, that was quite common until about the last 20 years. So what we've learned in the last 20 years or so by using scatterometer winds and microwave sea surface temperature, so now we're getting down into the tens of kilometers, and what it's shown is that the air-sea coupling is really different at scales of, say, 100 or less to 1,000 kilometers than on scales greater than 1,000 kilometers. If we look first at this figure on the left, this is from Larry O'Neill in 2010. So the colors here are the spatially high-pass filtered surface wind speeds, and the contours are in high-pass filtered SST anomalies. So the SST anomalies in the contours and the wind speeds are in the colors. And I think when you look at that, you can see that at those scales, there is a strong degree of correlation. And in fact, that when you look at the sea surface temperature versus the anomalous SST versus anomalous wind speed, you get a positive correlation between them. So the sea surface temperature and wind speed are positively correlated at these scales. What this means is that essentially mesoscale SST anomalies are driving the wind speed anomalies. So on the large scale, it's one picture. On the smaller scale, it's something different. So we have now a lot of effort and work trying to understand this eddy-mediated air-sea interaction. So this is the same figure as previously, except here we've done a global, this is Hyoreisio, published this in 2017, did a correlation between the high-pass filtered wind speeds and SST. So what you can see is now we have many positive regions of correlation. So the red is the positive correlations, and that indicates regions where the ocean is forcing of the atmosphere on frontal and mesoscale scales. So a little bit different picture has been emerging. So I'm going to make one final point about this, which is this analysis, and most of them that are done with with data are looking at the correlations between wind speed and sea surface temperature, which I'm going to show is only part of the story. So this is the high, if you want to think of it, we've been looking at high horizontal resolution. So as we start to look, at higher and higher spatial resolution horizontally, we begin to see this change in the correlation and how the ocean and atmosphere interact. And now I'm going to take a few moments and go through, if we look at much higher resolution vertically, and I'll start and I'll look for this at the ocean. So this is some work that we've been doing recently. So if you look in the ocean and you're looking under conditions of light winds, this is now a model simulation in which the winds stay constant for several days. There's the solar radiation is idealized. There's no rainfall. So here's depth in meters. So we're looking at just the upper 25 meters of the ocean for a few days. The color is the temperature. And what you can see every day is sort of this cooling and then warming of the upper ocean, then cooling a little at nighttime as the wind mixes some of the cooler water up, and then warming again and cooling and warming, and then an overall warming trend. And what you get from that is you look at the sea surface temperature itself, is you get a diurnal variability of about 1.5 degrees, a little under 1.5 degrees. And that then leads to, if you just look at the profiles again of temperature, so if we just take out one of these time periods and take out several days every afternoon, and you look up, what you can see is, the upper 5 meters or so of the ocean is pretty well mixed, and then you get this change down to the cooler temperature waters beneath it. And then it's warming up, a little bit every day. And the mixing that you get from this, now if you look at the turbulence kinetic energy, so how much turbulence is and mixing is going on in the upper part of the ocean, it's kind of, in some respects, the opposite of the temperature. When you get warming of that upper ocean, this is the time period where you really cut back on the turbulence. It dies down to a large extent when the sun finally goes down, then you get cooling and mixing of the surface, and the sun comes up, and you have just this diurnal cycle of deeper mixing, and then destruction of turbulence kinetic energy or lack of mixing as the day goes by. What we have had a little bit more time to look at is what happens if you have even lighter winds, so 0.5 meter per second. You begin to see there's a lot less cooling during the night times and a lot more warming of the upper surface, and now even more stratification. So our sea surface temperature warming is now like 3.5 degrees between what it is before the sun comes up and the peak value. And when you look at the temperatures profiles, now this is over 8 hours. We're kind of starting off over here in the early morning, and by 8 hours later is this curve here. And just to be clear, now this is at 1 meter. What you can see is that the vast majority of the change is in the upper 1 meter under these conditions. And this difference goes almost 6 degrees right through here, which has been seen. We can talk about this in satellite SST values. But essentially, what has happened is there is really no background mixing whatsoever. In order to get the model to even reproduce something like what is seen of these 4, 5, and 6 degree temperatures, we have to shut basically everything off but molecular mixing. Any more mixing than that, and it becomes very difficult to sustain this huge temperature change. But again, one of the issues is, notice there's at 1 meter it's about 26 degrees, whereas at the surface you're at about 32 degrees. And so that is a much more substantial difference with depth. So this is some work I did a little, a long time ago, as it turns out now. This is now, what I did from this one is I used a couple single column model set up for the Toga core, so tropical Western Pacific time period. So I had a high resolution ocean running under the NCAR, the SCAM model, the single column atmospheric model at the time. And what I did for this series of experiments is that I chose the depth of the ocean to basically to tell the atmosphere, to give to the flux parameterization so that the long wave flux and the latent heat flux and the sensible heat flux were using a value at a depth that I prescribed. So if we look to the left here, so this is the 4-month intensive observations period of Toga Core. So this is sea surface temperature. And so, every day we see these nice, strong diurnal warming events. This time period here was during the suppressed phase of the Madden-Julian oscillation, which is a 30 to 90-day oscillation that propagates through the tropics and becomes coupled with convection somewhere over the Indian Ocean. And typically during these suppressed conditions, it's sunny, the winds are light, followed by an active phase of the Madden-Julian oscillation in which the winds were much higher, it was cloudy, storms, and so what you can see during the suppressed conditions are, as you might imagine, low winds and high solar insolation, so lots of diurnal warming. Then when the active phase starts out, you get cooling of the SST, you see very few days with that diurnal warming, and then once it ends, it starts to pick up again. This uppermost plot is the skin value, which means, really our best estimate of that true interfacial temperature. This next plot down is at 2 centimeters in the ocean. For reasons we won't talk about too much here, but for those of you who are very fond of the skin, the cool skin effect, the skin is often about 0.2 of a degree cooler than just beneath the skin. So there's about a 0.2 of a degree difference between these two. As we go down a little further in the water column, this is about 0.5 meter down, and one can begin to see, a reduction in that diurnal warming during the suppressed phase. And at 4.5 meters, which was the depth of many of the measurements during Toga Core, there's very little in the way of diurnal variability. So I then took the basic run, and instead of coupling the skin to the atmosphere, coupled the 4.5 meter temperature to the atmosphere. Allowed the models to all run the same way. The difference is in what temperature I was giving to this. And I was thinking I might see some differences. But I was a little surprised at the differences I saw. This is the suppressed MJO time period. The bottom two plots are the active MJO time period. On the left are the temperature differences, and on the right are the humidity differences. So very few differences between coupling with the skin or the 4.5 meter during the active MJO, because they're not wildly dissimilar from each other. But when you look at the suppressed MJO, what you can see is that these are now, up to 4, and this is now the mean during the entire suppressed MJO phase, the difference. You see that the skin case results in a much warmer and more moist atmospheric boundary layer, and that in fact you see the ramifications of that kind of up through the column itself. So if we look at the diurnal impact of SST fluxes, this is just if you allow the ocean to warm during the day and calculate the fluxes versus if you sort of artificially keep it at the nighttime value, and this is 0Z to 3Z to 6Z, so forth. Every 3 hours, you can just see the progression of the warming from the sun, and you see aspects of winds picking up and so forth. If you just go through, this is now using the satellite data, and if we just take 10 years of it and say, in those 10 years at any given spot, what was the biggest difference between including the diurnal SST warming and not, this is what you see. So you can see values where it's 200, 300, and up to 400 watts per meter squared difference using that diurnal SST than not including that. And the mean effect on flux is then, so over 10 years, all time periods, it's 5 degrees globally, and it's over 5 degrees in the tropics. So when you're trying to get a balance, this turns out to be important. But salinity also stratifies the upper ocean. So this was data now from the NASA Spurs 2 experiment, which was located, this box here is basically where the ship was, and there was a buoy in the center of it, and it's really in the ITCZ in the Eastern Tropical Pacific. Here's just some data from the buoy. Here's the heat flux, so daytime peaks, solar radiation, nighttime loss of heating by the ocean, wind speed here on the right in the blue. We had conditions of up to about 10 meters per second, but we also had days where it really was about 1 meter per second. And the red is just sort of the rain that was just episodic throughout this time period. So if you look, this is somewhat analogous to the figure that I showed before, but using the real forcing data. And so this is the temperature, and you can see sort of the daytime warming and that real stratification again in just the upper meter. But you can also see that the impact that a salinity, a rain event has. You can see just the freshening of the ocean, a little bit of freshening. This was a large freshening event. And again, a large difference in just the upper few meters. There's another series of rain events towards the end of that time period, but the winds are much higher. So there's a lot more mixing through the ocean column. So given that there's so much variability in the upper part of the ocean, we thought let's explore how important that resolution is on the ocean side. So what we've done here is I've run a one-dimensional ocean model simulation for 30 days. And we're just looking at, there's no coupling. We're just looking at if you had the same heat fluxes coming in, but you had different vertical resolutions of the ocean mixed layer model, what would you see? So we had 3 resolutions. With 10 centimeter telescoping resolution, which I'll call high resolution here. Then I had it at 1 meter, and I had it at 5 meters. And what you can see is the difference between the blue is the high resolution, the 1 meter resolution, and the 5 meter resolution. And you can just see that the cooling that is different, even on the the long-term trend between the high resolution, the 1 meter, even the 1 meter and the 5 meter. Down below here is the depth of the picnic line, essentially the depth of the mixed layer. And the blue again is the high resolution. What you can see is just that even with a 1 meter resolution, you're not constraining that heating right into the upper part of the ocean, nor are you constraining that freshening that's also contributing buoyancy to the upper part of the ocean. And so when you don't resolve that, you get mixing much deeper, and that causes colder SST. And just to demonstrate that the sea surface temperature is a function of resolution only, if I take the high resolution model run and I just pull out the value at 5 meters from the high resolution run, that's this darker blue line, which looks exactly like what we expect to see. So it's not the fact that I'm just looking deeper at this 5 meter value, it's the fact that the resolution is different, and we're not really trapping that stratification near the surface. So this is, again, work by Hyode Seo, and which he was looking at the MJO with a coupled model, and basically showing that when you couple the model more often, so you're capturing the diurnal SST, you get more moistening of the atmosphere, and you have a different timing of your peaks of when your latent heat flux is the strongest. So when you have the diurnal SST, that peaks at about 2 p.m. and is stronger than when you are coupling the ocean atmosphere, say, once every 24 hours, and it's much less. So this is some work now that I've been doing with Eric Skillingstad, and we've been really trying to ask ourselves, does any of this matter in the long run, these kind of small variations here? And so we've run a coupled wharf ROM simulation. So the horizontal resolution is about 4 kilometers. And we're running ROMs for the ocean model underneath WARF. And because of constraints computationally, we have 2 simulations here that I'm going to show you. And one of them we call the high resolution, but I will emphasize it's at 1 meter vertical resolution, and low resolution, which is at 5 meters resolution. So this is the sea surface temperature from those 2 simulations. So the higher resolution results are on the left, and the low resolution results are on the right. One thing that you can definitely see is how much more diurnal warming there is on the in the higher resolution ocean simulation. I like to think of this as the lungs of the ocean. Almost like you can see the ocean breathing. And you can see it's breathing so much better when you have a little bit higher resolution. You're really capturing now what's happening at the upper ocean. And then just to emphasize, this is now a 1 meter vertical resolution and a 5 meter vertical resolution. We're not at a high resolution for the ocean model. Right now we're coupling the cloud LES to a series of one-dimensional high resolution ocean 1D models to try to address it if we had a higher ocean resolution. This is now the same thing, but surface salinity. So again, the high resolution ocean on the left and the low resolution on the right. And so just as you watch, again, in time, you can see a lot more of these freshwater lenses or pools of fresh water under the higher resolution, because again, it's doing a better job at capturing the fact that those are sitting at the top of the ocean and they're not being mixed down through the upper 5 meters right away. And so you can just see the difference in the number and strength of those pretty small scale rain events and their impact on the ocean. So the question that we should ask ourselves then is, what impact does that have on precipitation? And this is one of our initial steps on this, is to look at the impact on the precipitation. Here's a 10-day mean, and this is the accumulated precipitation. The blue is the 1 meter resolution model. And again, the difference in resolution is only in the ocean. So it's with a 1 meter ocean resolution or a 5 meter ocean resolution. And this is now zonally average, so latitudes here. And what you can see is that, after about 10 days, that accumulated precipitation, sort of that the peaks are actually shifted away from the center of the domain in the 5 meter resolution compared to the 1 meter resolution. So even impacting, even that little bit of difference that we're seeing between the warming and the freshening, when we couple that together, we're seeing differences in the convection and the precipitation field. So I've been talking a lot about vertical resolution. I'm going to switch back now to horizontal resolution, because one of the things that we are very interested in is how does the coupled system sort of respond now? Vertically, we realize we need to know very high resolution what's happening there. We also need to know across sea surface temperature front. So this is now the tropical Eastern Pacific, not too far from where the spurs 2 buoy was. We have these, this is sea surface temperature, so the cooler water in the blue, warmer water in the red. And there was a ship track that went across sort of, so warm to cold to warm, and looked at, now this is the atmospheric boundary layer temperature, and down below is the SST, so you can see that, as we're looking at the depth of the mixing and so forth, you can see that change in the atmospheric boundary layer as it goes across this, as you look over the colder water versus the warmer water. So to explore that a little bit, there was an experiment called KaiMode, which was the Clivar Variability and Predictability Mode Water Dynamic Experiment in the Gulf Stream. It occurred in 2006 and 2007. It was really designed to understand mode water formation. So there were some measurements of fluxes, and some Raywin sondes were launched from this. And so we can do a little bit of work. Now, I like to show this figure. This is what happens when you let the oceanographers drive the ship. So you get this kind of a ship track, which makes sort of interpreting things a little bit difficult. But we're going to pull just one component of it, which is really just this ship track right here. The sea surface temperature in the background. You're going to see across in the top part here where the ship, we start at the pink dot. The circle here is where the buoy is. So we're going to see the ship moving across. At the bottom figure, you're going to see is the latent heat flux, and it goes from 0 to 700 watts per meter squared. in the value. You will see a color. The color of the line is the sea surface temperature as measured by the ship. So you can see as this is going, so the cooler water, then it warms up a bit, we get higher fluxes, warms up again, stays pretty constant, and then we hit some warmer water and really warmer water, and we jump up to almost well over 600 watts per meter squared, which the change can be as much as 300 watts per meter squared in 19 kilometers. So one of the reasons that I want to point this out is that if we take sort of a similar ship track when we have lots of data and look at that, here's the latent heat flux change. So again, the color is the sea surface temperature in all three of these plots. This is the change in latent heat flux over the track. This whole track here is about 115 kilometers. Here's the change in the wind speed. You can see as it gets over the warmer water, it decreases. So this increase here in the latent heat flux is actually caused by the change in humidity difference between the ocean and the atmosphere. So one of the reasons that I point this out is that much of our work on understanding sort of the horizontal impact of variability has been looking at wind speeds and sea surface temperatures, but we're only capturing some of the interactions by that. That Airsea interaction really cannot be described entirely by the wind. And you can just see the differences in fluxes here. So this is distance from the front. The fronts are here. I just want to emphasize what I was showing there was a case of cold air flowing across warm water. So low latent heat buoyancy fluxes and then higher. If you go from warm to cold, the magnitude is much less, and it actually goes negative here as you're working to stratify the lower atmosphere. And this is again a cold to warm. Now we're looking at the Raywin song, and you can hear, so black here is on the cold side, then blue as we're getting closer to the front. The dots here are sea surface temperature, so you can see the change even in that tiny, from here to here, in just that last little surface layer just before the Raywin suns pick it up. And then the warming of the SST, and now you're starting to warm the lower part of the boundary layer. And then as you get to the warm side of it, just how much deepening. Now it's 1,000 meter mixing on the warm side of that front. Okay, and one thing that we have tried to look at is what do the satellites show us? And one of the things that we're finding is that many of the SST products that we're using for doing the fluxes, the winds, so again, the colors here are SST, but the solid line here is the ship's data, and then these triangles are the satellite data. So it's kind of tracking the winds, but the Airsea temperature difference is, in the mean is okay, but we're capturing almost nothing of that gradient, which is a key factor. So let me see, okay. So I will just say that I should point out the global mean water budget. If we use the original figures, the original figures or the original estimates are in white, and the blue numbers are what was needed to balance the terms. So you can see it was about a 10% difference between what we thought the ocean evaporation was, what our satellite estimate was, and what it would need to be balanced. I will just point out there's a new version of our Flux product, which I'm going to show you in just a moment, and it's closer to the balance value, which is somewhere around 450, and we're definitely above where we were before. So progress has been made. But if we really want to understand the global trend in ocean evaporation, this is a number of different satellite products. So these colors are for different satellite products. OA Flux is a blended product. Red OBS are a series of models that use a very limited set of input observations to drive them. So this is now the anomalous latent heat flux from 1980 through about 2020. I'll just let you look at that and see if anything strikes you as like a really consistent trend from any of the products, and just the differences between them are kind of astounding. So trying to use them to understand trends, we still have a ways to go. And this is just the same figure, but now with the reduced obs. The fact that we're using the mean of these three models is not causing that lack of variability. They're very, very similar to each other, and all of them tend to be much higher in the mean, even than the satellite products. So still some work to do. And if we look where the products are most different from each other, this is taking the 5 products and seeing where they're the most different. The red and the yellow is where they're the most different. Often this is in the frontal or eddy regions where we are most uncertain, and that's because we can't see winds, temperature, and humidity at these scales. So I'm going to take about 5 more minutes, and I'm just going to do a quick, some of the things that we're doing to observe air-sea interaction. So a lot of it is autonomous, drones, things on the surface, sail drones, wave gliders, working towards getting better lidars of various kinds. This is something that I helped develop here. It's called the XBAR. We'll look at that in just a moment. We put it out for a first long deployment this last winter in the North Atlantic, because why not pick the most extreme part of the ocean? So it measures, you can see it sitting up in the water, so it can measure, it's actually directly measuring the fluxes. So it's getting turbulent measurements of moisture and winds. And we just happened to be sitting there when Epsilon came through. And so here's the wind speed. So getting 22 meters per second in the first band of winds. We're getting significant wave heights of 10 meters. And as time goes by, that we can really resolve that cold front that comes through. There are lower winds, a shift in the wind direction. There we go. The wave heights again exceeding 10 meters in the next band of storms. And then we drift into the eye of Epsilon. So the winds just pretty much completely die down. You see this in the shift in the wind direction. And we measured long, various bands of strong winds when the storm was no longer recognizable. So this is just an autonomous float that we put out. We have a local air-sea interaction tower. That's the picture of it on the right, just off of Martha's Vineyard, that we have been utilizing to make a lot of high-quality turbulence measurements, including an experiment where we're measuring fluxes within the atmospheric boundary layer and between the atmospheric boundary layer and the oceanic boundary layer. We have an upcoming project with the Department of Energy. So this is now the same tower. It sits here. This is a map. There's Massachusetts up here and Rhode Island. Here's Martha's Vineyard. So this is where the tower is. The Pioneer OOI buoy array is down here. These colors are regions where the wind farms have leased out. And so we're going to do an intensive observations phase. We have lidar buoys that are being put out. We're having a barge with another tower on it being put out and trying to do a better job at really doing the coupled boundary layer system. The goal, of course, is to try to get some kind of system where we're really resolving the atmospheric and oceanic boundary layers as a coupled system. And the last thing, which was already mentioned, is our Earth Venture mission proposal of Butterfly. Shell Gentleman is the PI. I'm the deputy PI. Our project scientist is Tony Lee, and our deputy project scientist is Shannon Brown here. So we've got the close JPL with a number of other institutions as well. And the whole goal of this is to do a higher resolution and fully measure all the things that we need to calculate the latent and sensible heat flux from one satellite system at less than 25-kilometer resolution, so that we can look at not only how the high resolution fronts and eddies impact back on our weather and climate, but also how resolving this may improve our satellite observations in general. So just some final thoughts. There's continued improvement of resolution in observations and models that's demonstrating the strong scale dependence of Airsea interaction. We really do need process studies aimed at the coupled boundary layer system at high vertical and horizontal resolution. The models are kind of outstripping our observations in terms of resolution, and being able to address these with satellite observations would really be helpful, and might improve also our climate data records. And what else might we discover as we keep looking closer and closer at this coupled system? So I'm going to stop there. This is I'm ready for any questions and questions that you may have for me. This is the deployment of that XBAR buoy that I mentioned. I just want to give a shout out to the team that went out on this. Not only did we have to finish the preparation of the buoy under sort of COVID conditions, to even go out on the ship, they had to a hard quarantine for 2 weeks before and 2 weeks after. So what was originally supposed to be a 5-week cruise turned out to be 9 weeks total that they were gone. So I'm just going to let that play. As you can see, putting out the 14-meter buoy, you only saw the top half of it above the water line in the pictures. So I'll let that go and see if there are any questions.
Thanks very much. I actually can't even watch that video because it makes me feel a little bit queasy.
I have a video where that a colleague took of when they were down in the Southern Ocean, and I was explaining why certain things were happening, and it's from the bridge, and I was doing it at a show at something for teachers, and so it was and one of the teachers got up afterwards and called it the vomitorium of a video. So
yeah, I'm gonna just hide that. Yeah. We do have a question in the chat. Thank you very much for that. By the way, it's hard. We all would love to be applauding that. That was very interesting and very accessible and very thorough. But we do have a question from Evan Fishbein, and I will actually, it's 2 questions, but I'll read first. I'll read them both, and you can answer as you wish. The ocean heating is the difference between shore wave, long wave, sensible, and latent heating, i.e., heat deposited into the deep ocean. First question. And then the next question is, does the MJO simulation include precipitation with changes in near-surface salinity and wind gusts from precipitation?
Yes. Okay. So to answer the first question, yes. So the ocean is gaining the heat through all 4 of those fluxes that Evan, that you mentioned: the short wave, long wave, sensible heat flux, and latent heat flux. All 4 of those impact onto the ocean. And the second question about the MJO, it was a fully coupled model, so that changes in salinity in the upper ocean did impact back on the sea surface temperature, through reduction in mixing. That change in SSC was then included to changes in convection and precipitation.
There's a question from Ben as well. I don't know, Ben, if you want to unmute and ask. I know that Evan can't do it. Typically, he's got audio issues. I'll go ahead and ask it. From Ben Holt, have you encountered biogenic slicks in your fieldwork and studies and noticed any impacts in Airsea fluxes?
I'm sorry, can you ask that again? So biogenic...
have you encountered biogenic slicks in your fieldwork studies and noticed any impact on Airsea fluxes?
So that's a really good question. So surfactants, how those impact back, they do, and there is some work on that. It probably doesn't seem to impact it enough to make sort of on the global scale variations, but they can impact back on the fluxes in several ways. And one is any changes to stability of the upper ocean will change sea surface temperature, and also anything that changes the roughness of the ocean surface changes both how the heat and moisture exchange, but also the momentum exchange as well. So it definitely takes a lot of different observations to fully look at how these two fluids are interacting with each other. And that's probably one of the most difficult aspects of this, is to really capture all of that. If you need a sort of a complete physical, biological, chemical, high resolution vertically and horizontally. So I skipped over just a little bit. Since we've got the X bar, this is what actually I proposed as an ocean shot to the National Academies, trying to do long-term what we're calling super sites that are taking advantage of like floating wind turbines, and where we are with autonomy now, and trying to capture as much as we can of sort of the coupled system as a whole.
Okay, I want to just say myself that I think you're going to need to get another solar array on your butterfly satellite. There's a question from Jorge. Hi, Carol. Thank you for a great presentation. Do you think it would make sense to identify time periods when one has clear infrared imagery and do the gradient calculations and flux comparisons? Do you think it would make sense to identify time periods when one has clear infrared imagery and do the gradient calculations and flux comparisons? My concern is that there can be periods of times when cloud cover prevents calculating the full resolution of the FST gradient.
Thanks, Jorge. Yeah, and you know quite well that 25 kilometers is not the best resolution we can do in SST, right? We can do much better than that. And one of the issues is that the flux products themselves need a complete and entire sea surface temperature field, and so it tends to use either a Vis-IR microwave blended or just simply a microwave product. So yes, we're looking at sea surface temperatures that are 25 kilometers, and if they're blended, then often it's if you're using the Reynolds, it's kind of optimally interpolated, and so you're continuing to sort of smear out the ocean surface. So one of the problems is that we can do much higher resolution on the sea surface temperature, but we can't do much higher resolution on the other components. So we're sort of at 25 kilometers for those values. We are working on, and I know that some of you even on this call can do some tricks to try to get like the winds down to less than that. We're actually right now trying to play around with a high resolution version of sea flux, in which we use a higher resolution sea surface temperature, and how if we use that in combination with even the 25 kilometer air temperature and humidity fields, does that show something a little different? Good question.
Okay, Evan, do you want to go ahead and ask your question? We can't hear you, Evan, if you're speaking.
Hi. Okay, so so I wanted to follow up that question I asked earlier about the ocean heating, and it may have been addressed by one of these maps you showed. But the question is, during the first decade of the 21st century, there was sort of a hiatus in warming, and my understanding is that's attributed to the deposition of heat into the deep ocean. And I was wondering if you have a feeling for where, if heat gets transported into the deep ocean, does it tend to occur in eastern boundary currents or western boundary currents, or in the tropics?
So that's a good question, and I'm thinking that when I haven't looked at that, like the most recent work that's been done on that. So I'll just give it as a caveat. A lot of that exchange there was a lot of focus on the tropical Pacific for where that uptake of heating might be, and that you are absolutely right that one of the discussions or one of the possible causes of the hiatus was, that the deeper ocean was taking up more heat than the upper ocean, and there does seem to be some change associated with that, and that is one of the possibilities.
Okay, but don't you get greater in the eastern boundary currents, don't you tend to get greater, stronger upwelling? And wouldn't those be the places where you'd probably be most able to transport heat into the deep ocean?
Well, the best places for transporting heat into the deep ocean are actually the deep convection. If you really want to get to the deep ocean, that's where you get convection down to 1,000 meters or more of that. But in terms of where you might have this heating, some of it has to do with it as you change or change the trade winds. So you have differences in Ekman pumping. Excuse me. That will make an impact. I mean, there's a number of dynamics that go into that, and we really are talking about things, more than just sort of the very upper ocean now, and getting the heat down deeper.
So I just want to thank you for this talk. The only problem is it's actually a semester-long class, not just a 1-hour seminar, but it was very interesting.
Thank you, Kevin.
Okay, does anybody have any other questions they would like to ask? You can unmute yourself. I know that you have a number of other talks or other meetings today with some groups and individuals, but in case somebody has a question they want to ask now.
Hi, this is Ron. Can you hear me?
Yes.
Yeah, just thank you for a wonderful presentation. It was great. Looking forward to meeting later on, and I hope you enjoyed the meetings today. Thank you.
Did you have a question, Joe?
No,
Thank you. Oh.
No, I have a lot of questions, but I'll ask them when we meet. But I just wanted to explicitly thank you for the great presentation and agreeing to do a virtual visit, which is, as you said, not ideal, but I think it's going to be very positive anyway. So thank you again.
So, and I'll just call you out, Joao, right now, and thank you again for your leadership of the NASA PBL study team, and yay, the release of our white paper. If any of you haven't seen it yet, ask Joao. He can send you the link for it. That was a lot of work, and I'm hopeful that there's going to be a lot of great science that comes as a result of giving this information to NASA. Thanks, Joao.
Yeah, thank you. Thank you. You're too kind. Was a lot of work for everyone. Thanks for your support. Hopefully people will find it useful.
Yes, and having this virtual visit doesn't preclude a future in-person visit. So if you have maybe some more results or something more to say about butterfly at some point in the future, we can organize that perhaps. So if we don't have any other questions, it doesn't look like anything else is in the chat. We have several people saying thank you for a great talk, from Dan and Terry Kubar. So we'll capture that, and we can send you the comments from people. But thanks again, and with that, I guess we'll close out the meeting today so that you can get on and start your in-person meetings.
Great. Thank you so much, everyone. And I look forward to the meetings the rest of the day.
Okay.
Thank you, Carol Ann.
Thank you.
Bye-bye.